Today we are going to talk about big data and data science, these four words which will sell everything today. But again, I will explain why we will talk about this and how they are basically connected together. I'm a CTO of a quantum company. My name is Alex. So a few words about the company. Maybe not about the company, but about the data science department. We opened the data science department 3 years ago. And after these 3 years, we managed to complete dozens of projects, because in data science projects not always big, so they are maybe small. And throughout these years, we've seen some trends emerge, and about these trends we want to talk about today. I will describe a bit which trends we see in data science area nowadays, and then present you 2 use cases which actually adhere to these trends and show exactly why I think these trends are happening. First use case will be about the epilepsy, but at first I want to talk about big data. So big data may be a bit misleading. So if I ask somebody what is big data, if I don't know, 1 gigabyte is big enough or 1 terabyte is big enough, then they said, okay, 1 terabyte is probably not a big data, okay, and 2 terabytes is big data or not. So what basically is big data? And the answer to this question is that big enough for what? So people think that big data is big enough to make it troublesome to process this data. So I want to give a bit different meaning to the big data in this talk, is that big data is big enough to make some end-to-end models work. But usually these two are come together, so when you have big data enough to make some model work, you usually have troubles to process this data because it's too big to process. So anyways, here is a trend we see, that different projects we take part in are on one of the 3 stages. So the first stage is when you have simple rules. So for instance, you have a factory, you have some machinery in there, and you have a simple rule. Okay, if the temperature of this machine during the 5 last minutes is bigger than 50 degrees, then you should turn it off. So that's a simple rule that works throughout the world right now. So, but then they started to move to the feature-based models, is when experts start to think, okay, maybe we should make logic be more agile, so they introduce some rules. They introduce some features, so they take temperature during the last 5 minutes, they take vibrations during the last half an hour. If you, how many times you hear some strange sound from this machinery, you put this as another feature, and then you make some classifier. Okay, this classifier that says, should I turn the machine off or everything is okay? But when you collect a lot of data, you probably do not need to collect these features anymore. So you do not need this expert who will think, okay, what is important to make this decision? And you start to feed the data you have into some model which decide what is important and what is not. And during the last 5-10 years, in many areas, we collected enough data to move to the third stage. And the first such area is medicine. Where we took part in the project. This was a half-year long project where we classified epilepsy patients. So a bit background of the subject. There are 2 kinds of patients with epilepsy. One of them are drug resistant and the other are not drug resistant. What means they are drug resistant is that if they take some pill, it doesn't help. It has some short-term effects, but after a while, they still experience the seizures, and they need to switch to another drug. So for other people, which is a majority, maybe 90% of them are non-drug resistant, they just need to increase the dosage over time, but they feel okay with one kind of pills throughout their lives. And the other input I want to give about epilepsy is that nowadays we do not know a lot about this disease. So the only thing we do is to minimize the seizures, but we don't understand the mechanisms that is happening behind this, why we have the seizures. So our task was to improve the classification between these patients. And why this is important is that patients that are drug resistant, they need a special treatment. They do not need to switch pills over time. They need sometimes even surgery. to make them live fine. And nowadays, in order to be diagnosed as a drug resistant, you need to spend 3 years in a hospital taking some pills that don't help you. And we try to minimize this time. So we try to classify a patient as a drug resistance after 1 year or maybe 2 years, and not make him suffer for 3 years. So what we have as the input? There is a group of data scientists working with a pharma company who were trying to make this classification. And they engineered 3,000 features. So what kind of features? These features like whether the patient took pills last 30 days, or whether patient had seizures last 90 days, or what is the dosage of this pill during throughout the year, something like this. So 3,000 such features, which they think may help us classify the patient to be either drug resistant or not drug resistant. And they worked on this throughout many years, and throughout these years it was possible to collect the data about patients. So it's a bit difficult to collect the data because this is not standardized throughout clinics. And for instance, if you come to Germany, you do not have such data at all. In USA, this is possible to collect such data, but from insurance. So we had claims data for 450,000 patients. So that's quite a lot of patients. That basically means almost everybody who has insurance in US. That means almost everybody in US. And this claims data basically contains information about diagnosis, procedures, and drugs prescribed. That's what insurance pays for. So what we did first is that we took 55 top features. So this scientist built a model, simple model, just for logistic regression. They switched it to XGBoost and produced a model that worked fine. But our task was to improve this model. So first of all, we built a baseline model with XGBoost and used the top 55 features they provided. And we were able to make the same result as they did. So that was like ROCOOK 0.77. So I believe you know what is this ROCOOK because you are like data scientists. So okay, so that's basically the quality of the model, some trade-off between precision and recall. So, but anyways, we just took 55 features, and so I'm talking about the left side of this diagram. Just took 55 features and feed it into the boosted trees and got this result. So that's a baseline. Then we thought, okay, what we can do if we just add some information from their treatment history. So what we did is that we took treatment history for patients and encoded this information. How we encoded it? So treatment history consists of some codes. These are standardized codes, but we didn't want to encode them like bag of words, one-hot encode. We wanted to give them embeddings. So we used the claimed history as a sentences and used the same skip-gram model to give them embeddings. So basically, drugs or diagnosis or procedures prescribed to the patient in the same context would obtain the close embeddings. So in this way, we created embeddings for these ICD codes, which represent diagnosis and procedures, and for drugs. So drugs, they have their own codes. And then we just did like global pooling on them and obtained 200 more features, which we feed into the same decision tree. And what we get is that ROCOOK increasing into present. So what does this mean? Is that means that scientists, despite they worked many years on this topic, they missed some information that contains in the claims history. So they didn't catch with 3,000 features what's in there. They just were not able to do this because it's like was too complex. And that gave us a clue that this claims history contains some information that might help to improve this classification. And what is 2%? Actually, 2% is that on the 450,000 people, like 10,000 people. So then we moved to a bit more elaborate models in order to improve the quality of the model. So what we did basically is that we created a deep learning model where we used embeddings and SWAM so I will not dive deeply into the SWAB model. And the final model was a bit more complex than this one, but still what you need to figure out from this diagram is that there was a deep learning model, and we had these 55 features we had already, and we created the deep learning model that produced more features, and pushed it into the fully connected classifier. We need to have fully connected classifier to make it train altogether. And then what we obtained is that we increased ROCOOK to 0.81, so which was like state of the art in this field at the moment. But that's not so interesting. So the interesting experiment that the farm company asked us to perform was the third one. So the third one is the same as the second one, except that we get rid of 55 features from the experts. We leave only age. So age is what you cannot find in the claims history. Everything else you can find there, except some information that they asked us not to include in there, like gender and like zip codes, just because of privacy. And what's interesting about this model, so maybe somebody can give a clue what's so interesting about this model. Okay, so the interesting thing about this model is that we do not use the information from experts. So you need to understand that we are not experts in the epilepsy disease. Of course, we know some information about it because we worked half a year on this project, but still we are not like doctors. We don't understand at all the epilepsy. We know like a little bit more than everybody else. And we just created a model and fed everything we had for 5-10 years for patients, and we obtained the ROCOOK 0.80. And if you compare this to ROCOOK, which scientist obtained after several years of work, which was 0.77, you understand that this model was able to perform better. And that's not because we are so clever, that's because we had so much more data they had at that time. And this data couldn't be processed manually. And that was like amazing result because in half a year, some batch from high school didn't know a thing about epilepsy could produce such result just because industry produces this data. And that makes they think how to standardize the collection of this data, because we were just lucky that insurers had this data. Clinics do not collect this data. In Europe, you don't have the data at all. I don't know about Israel. So, and then we started to look into cases and analyze in which cases patients are drug resistant. And we figured out, for instance, that some patients which had depression and took pills from depression are likely to be drug resistant. So this knowledge is something that wasn't known before, even for experts working in this field. We don't understand why people suffering from depression are drug resistant. So we are not doctors, and even doctors do not understand why. But statistically, we have proven that, okay, there's some piece of information you may use now to better understand this disease. So that's valuable. And we figured out a bunch of such information that we passed it to the experts. So before we move to the next case, maybe somebody have some questions regarding this one. Yes?
Did you actually give the data to experts, and what experts say about these new features extracted? They help them?
So we didn't extract new feature, we just build a model. Okay, let's look a bit on this model. So on the top you see that we feed, we mix all information from the claims history and coded the ambulance. So what is claims history basically? Here it is. So for each patient, what we have is the information about the date, some code. The code may represent a procedure or a diagnosis, or the code may represent some drug, and actually code type. And this information is mixed and then sent to the SWAM model. SWAM model, it produces as an output just a 200 size vector.
But now the expert can better predict something about the patient with the disease?
Yes, basically now the expert can predict better, but it doesn't mean that he understands better why he is drug resistant. So these features that produced by SWE model are not interpretable. So it's not like if you have a feature whether patient is older than 55 years, that means something to you. If you have some feature in the after the same model, it's just a number, you don't understand what does it mean.
I don't want to understand, I want to predict only to give better solution to the patient, so it can be done.
Yes, it can be done. So at the moment we are on the stage of the certification of the model. So in US you need to certify a model to be able to use it. And this model is about to be deployed to the Symphony. Symphony is the organization which actually collects the claims data. It has contracts with the insurance companies. And it sells this data to pharma companies to make analysis. But if you want to provide something for doctors, so they can, some therapists, physicians, you need to deploy this model to Symphony because the Symphony produces interfaces for clinics. So that's the kind of the stuff that happens in US. But we met a bit of a problem with certification of the model, because in US, when you have in US they have laws which prescribe you to interpret your results. For instance, when you want to have a loan, bank cannot give you a loan, but a bank must describe you why. So he says, okay, your income is lower than this one. That's because you don't have a loan, and that's in the law. And here is the same stuff. So you need to say why you think patient is drug resistant, and the interpretability of the model, such deployment model, is a bit of a challenge. So that's another project, how to interpret the results. So if you have logistic regression, everything is simple. You have these results already, yes? If you think the patient is drug resistant, you say, okay, that's because he, I don't know, he is a woman, he is older than this one, or he takes these pills, and they are not successful. Because of this, I think he is drug resistant. In this case, you just fed all claims data in the model, and it says, okay, it's drug resistant, but why? So nobody understands. So now we are about to certify this model, but that's a big complex stuff, and in order to do so, first of all, we need to solve the task of interpretability. So there are some frameworks that allow to do such a thing, such as Sniper, for instance, and you even can use it on your PyTorch and TensorFlow model. But in this case, we built custom layers, and this doesn't work out of the box, so we need to spend like 3 months more just to make something that can interpret results. And again, maybe we may not solve this task at all. So it's not like just about the time. And about the big data in this case. So as I told you, we have claims history for 450,000 patients for 5-10 years. So you may imagine that's quite a bit. So for each patient, we had like ranging from 100 to multiple thousand of entries. And to train such a model, we spent 2 days, and that's not such a crucial number, but these 2 days were spent not exactly on training the model, but just on gathering the data from the Azure warehouse. So we needed to spend 2 days to go through the data multiple times to train the model. So that's why it's what was so slow in training, but it was like not so heavy model in inference mode.
One more question.
Yeah.
Why did you use here the embedding procedure on the? It was on the names of the drugs, right? Of the treatments.
It was not on the names of the drugs. So if you want to fit something into the model, you need to represent it as a number. You can't represent it as a code. So obviously, yeah, you can do one-hot encoded, but in this way you lose information. It's the same way you lose information when you one-hot encode words, because words may be synonyms, they may be used in the same context, and you want to represent this information in some way. One-hot encoding loses this information entirely. So here the problem was about losing such an information, as the first thing. Another thing, the space of this vector would be really huge because we had too many codes for the diagnosis and the procedures and too many codes for names for drugs. And in order to overcome this, we
assume that the codes have some space that the range of the codes or something are close to each other because there is no information in the code, right?
Yes, there is no information in the code itself. But what we did is that many patients have some treatment history. So you may take this treatment history as a sentence, as you do this real sentence, then you can build embeddings for words. So for words that are met in similar contexts, you will give the similar vectors. In this case, so imagine that patients had similar diseases, and for similar diseases, they were prescribed with similar diagnosis, procedures, and drugs. So, but they may differ. So we see, okay, this patient has the same diagnosis as this one, and the same procedure, but a bit different drugs. But maybe these drugs are similar in their effect. So in this way, we use the same Skibra model to represent all these codes as vectors by their context.
So you describe the treatment as a sequence?
So yes, we describe a treatment as a sequence. So we take the treatment history for one of the patients, and then we encode each entry as a 100 size vector. And then we fed this list of vectors into the model. So this can be different models like LSTM. So we tried LSTM as well, but the problem with that was that it didn't handle long sequences, like multiple thousands. So it did lose information. What?
You entered it to the word of it, to the embedding.
After the embedding is built, we just have a list of vectors, and that's it. So you can fed this list of vectors to every model that can receive the list of vectors. This can be RNN, this can be any other thing. So for SWAM model, there is a paper in the internet, you can find it. So this called, so the SWAM, this called the simple word embeddings model. There are 3 kinds of them, so we tried all of them, and the final model is a bit more complex. It's like stacking of multiple models, multiple SWAM and one CNN. But still, that's not the point of this presentation. So the point was that we were able to achieve better results than the experts. So you may invent any other model, and the model is not so important basically. So the importance here is the data. So you can copy the model, but you can't do anything with it because you do not have access to the data. So the data is real value in this case. Okay. So the next thing that is possible nowadays because we have data is another project we made in the area of agritech. So that's about the deforestation. So deforestation, when you cut the trees in insane amounts and then you don't have trees in the amount you want. So despite Ukraine has lots of trees, so basically I am from Kharkiv, and Kharkiv was built in the middle of the forest, so it was cut inside of it and then just grew. And we have trees a lot everywhere, so that's like not a big deal for Kharkiv citizens, but still what we are fighting here is not with some insane tree cuts, insane amount of tree cuts. What we are fighting here is with tree cuts in prohibited areas. And before information from Sentinel was available publicly, it was not possible to do this at all, because what people did previously is that in every single village, in every single place, you need to go to forest and see whether somebody cuts trees there or not, and prohibit this in some, and enforce these limitations in some way. But nowadays, we have Sentinel-2, which just flies multiple times per week around the world, and what they did is that they made this information public accessible. So it's not so, if you want a bit more quality and frequency, you need to pay for it, but if you just okay with one image per week, then that's fine. And if you fight with 3 cuts, probably you don't need more frequent than one per week. So and the quality is like 10 meters, 1 point is 10 meters size. So that's quite enough to actually find the triggers. Okay, so that's how data flows in this project, and the main point of this diagram is not to make you read all this stuff, is that the main point of this diagram is that it's not like you just take a picture from Sentinel, apply a model, and produce a result. So when you deal with imagery from Sentinel, that's again quite amount of data. And you need to process this in background, you need to apply a model in background, you need to cache these results in some database that allows you to search by some shape. So for instance, in this field, what pictures do I have? So for instance, here we use PostGIS for this. And yeah, that's one of the examples where the amount of data makes it tricky to process it, and you need to do something about it, some layers of cache and stuff like this. So okay, so and Sentinel provides you with a bunch of channels that you may use to analyze whether you have triggers or you have like a healthy trees in there. So that's like RGB, near infrared and NDVI. So it provides not NDVI, it provides infrared and red, and you can calculate NDVI, but that's not important. As well, in Kharkiv we have a lot of universities that produce a lot of students that you may use to label data. And use a bunch of data scientists to make a model, label it by students. Yeah, we cooperate with a lot of universities in the city, not just for this purpose, of course. So yeah, then we use not a simple UNet, so here is just a picture of UNet, but a bit modified version of it, and this was enough to produce information about the triggers. So here you can see a picture where with the red areas, we show fields where there were trees, and now there are no trees. And then this information is sent to the authority that has, I don't know how to translate in English, but they have a list of areas which are prohibited to, where you cannot make a tree cuts. And now they can actually go there and see by themselves what's happening in there. So this was one of the examples that was not possible before, and one of the examples where nowadays you have a data that you can use to provide something that's not just automates the human work, but that's increased the value and makes it possible was not possible before. So other stuff that is now available in agri-tech are drones, of course, satellites, some machinery. Every machinery has sensors in it. So for instance, if you use John Deere, there is a service that has contact with John Deere, and you may upload the file from the combine, for instance, and they parse it and provide you information where it was, what it did, so you can analyze this. That's not for free, but still it's like manageable. And of course, you may use some sensors in the field. That's really actual for some greenhouses where you don't have drones or satellite images. And now what we see is that after 5-10 years, the amount of data collected in the agri-tech is enough to provide some end-to-end models which will increase the possibilities of what agriculture can do nowadays. For instance, you may even increase precision and work with each tree. So for instance, nowadays it's not possible manually to go to see how each tree is growing, but nowadays it's possible to see whether some tree needs irrigation or whether some tree needs some special treatment or have a disease. So you can work on the tree instance level just because of the drones. So satellites, of course, do not allow you to do this. Satellites just 10 meters precision. So and even you can use sensors which you put on the leaves to analyze its temperature. So satellite can provide such information, drone as well. So you may wonder what is common between these cases. So of course, such cases, as I told before, share the problems or tasks how to build data pipelines. Because in both of these projects, it was tricky how to process such amounts of data. And when you try to build end-to-end model, you always, no, not always, but almost always have such a problem how to deal with such a big amount of data. And you do not, and you need to have a data engineer in your team to do this. So data scientists are good when they provide some model, but in order to productize this, you need the data engineers that will build the data pipeline. So another stuff is data privacy. It's not so relevant to the agri-tech, but in medicine is really hot topic. As I said, we even needed to remove zip code from the model, for instance, just because that's against HIPAA. And a lot of such stuff will arise in the future when people will see what they expose, actually. And I believe in agri-tech we will hit the same problem eventually. So the third task is results interpretability. Even in agri-tech, when you say, okay, this tree have some disease and needs some treatment, you need to provide VIUC. So for some cases that's obvious, for some cases that's not. So you've seen that, for instance, NDVI level is lower, so you need to report to the man who is responsible for this area that, okay, so you need to irrigate just because of it. And not just say, okay, irrigate it. So because models as well, they have some amortization, and maybe nowadays it works fine, and in half a year it will just make these people irrigate everything just because data is not relevant anymore. And as well, model certification. So, okay, in the healthcare, that's really sensitive, and it's really new. For instance, in US, they came up with such law just about, I believe, 9 months ago. So that's really new, and I believe in every area where we will implement end-to-end models, we will come up eventually to the point where authorities will introduce some laws how to certify what you are doing, because otherwise it will just like models that produce some results which you may believe or may not believe, but that may influence somebody's lives, and you need to regulate this in some way. So that's a common task, but the common trend which we see is that nowadays more and more areas collect the data which is enough to build end-to-end models. And we see this in medicine, and I believe in Europe they will collect the data as well eventually. And we see this in agri-tech nowadays, so we see more and more projects in this area. And this will be commodity in other areas. And the role of expert in this case will be not more to generate these features. This will more to analyze the results of these models. So as well in healthcare, we provide results. And at this point, we try to certify this model so it's not in production, but experts use this to better understand the disease. So they like use this model for their own needs, but they don't make this model anymore. Okay, that's it. Questions? Wisdoms?
I don't even understand. When you say certification of a model, you need a certificate to use the model, or you give a certificate to one who uses your model?
Okay, that's specific right now to the US healthcare. And if you implement the deep learning model, you need to certify it in order to use it and to recommend something to the physicians. And at the moment, there were 2 cases of the models that we were dealing with imagery that were certified, because the law is raised new. And this model doesn't deal with imagery, it deals with data analytics, and there were no models dealing with data analytics certified in the US at this point. So we're like trying to make a new road there. There are different other cases. So for instance, you may make a recommendation system which will say, for instance, okay, I think this patient is drug resistant, pay attention to these features. For such model, you do not need the certification, because you just recommend. So when physician thinks, okay, maybe this patient is drug resistant, model suggests me he is, what should I pay attention to? that's you do not need to certify. But in this case, you need to interpret the results of the model. You need to point to the physician why you think he is drug resistant. And there are other cases, for instance, when so there were some proof of concept for a project where people provide analysis to a doctor, which need to say, okay, this patient has this type of cancer. And then they need to take a biopsy. Biopsy is something you take without anesthetic, so it's like painful. And if you miss, so you don't get the kind of cancer, you need to do another biopsy, so that's painful. So in this case, we provided for this. So the main requirement in this case was model interpretability. So we needed not just say, okay, we think this type of cancer. We just needed to say, within this type of cancer, pay attention to these results of the analysis. So the physician, if this result was not what he had anticipated, he just checked it one more time what model suggested to check, and that's it. In this case, you do not need to certify a model because it doesn't make a decision. It just suggests to do a second check on the patient, and that's it. So yes, so there are different cases where you do not need to do certification, but still for the models where you cannot right now interpret results and you really suggest something for the physician, this must be certified. I hope this answers the question. Okay, I think that's it. Thanks for attention. So here you can find some contacts. So yeah, so if you have some additional questions, although you may find me here around, I believe next 30 minutes or so. Okay, thanks for attention.